In this video, we're going to discuss effect size. So Cohen's d is not new. We saw that when we were doing our hypothesis test using the z-score. Now we're going to look at effect size for the t statistic, and the first one we're going to look at is Cohen's d. So the estimated d is the mean difference, so this is the measured difference, how far away our sample mean was from the population mean, and then our standard deviation, which is our expected difference. And again, remember, Cohen's d takes out the idea of sample size, and so that's why instead of using the standard error, or the expected or estimated standard error, we're using standard deviation now. So from earlier, if you remember that, so here's an example from earlier. This is that teacher-led example. So if you go back to that handout, follow along and try to calculate Cohen's d along with me on that handout. So here I've just changed it a little bit, and I added in, because we had calculated earlier that our standard deviation was 3.34. So we just need to plug these items into our formula up here. So for our Cohen's d, our estimated d, we're going to use the sample mean of 9 minus the population mean of 6 over our standard deviation, which is 3.34. And that should give us a value of 0.89. Now that's a pretty large effect size if you remember looking back at, so an alternative for measuring effect size is to determine how much of the variability in scores is explained by the treatment effect. So if we can measure how much of the variability is explained by the treatment, we'll obtain a measure of the size of the treatment effect. So it's just a different way of looking at effect size. And you'll see both Cohen's d, this r squared, represented in the literature. And this is again kind of that move towards those new statistics, is making sure that we're reporting effect size in addition to the null hypothesis significance testing. So in order to calculate r squared, we need to have our t statistic that we calculated from earlier on. So if you look on your paper, you should have a t-value of 2.54. So this is our calculated t, not the critical t, the calculated t. So we're just going to take that 2.5, so we're going to plug it into that formula. So our r squared is going to equal 2.54 squared over 2.54 squared plus our degrees of freedom. And if we remember our degrees of freedom, we had an n of 8, which means our degrees of freedom were 7, or n minus 1. So we're going to do a plus 7 here. So this is going to give us 6.4516 over 6.4516 plus 7. Which is then 6.4516 over 13.4516. And that ends up giving us an r squared, when we do all the calculations, of 0.4795, or 48%. So that's the percentage of variance that can be explained. So just let me erase this here so you can see that. So 0.01 is a small effect, 0.09 is a medium effect, and 0.25 is a large effect. So we have a very large effect. We saw that with our Cohen's d too, is a very large effect. So another way of looking at effect size is measuring a confidence interval. And so a confidence interval looks at the values around that mean and says, how confident are we that those values, if we were to do another sample and replicate this, that these samples would fall between these means again. And so it's estimating the new population means from the sample mean. And it does that by rearranging the formula here. And so we're going to get a plus value and a minus value. So we're going to take that sample mean, and we're going to take the t-score based on whatever confidence interval we decide on, and then we're going to use that estimated standard error. So it's based on the reasonable assumption that the sample mean should be near the population mean. The interval constructed defines near based on this estimated standard error and allows us to confidently estimate that mean should be located within a certain interval. So in any t distribution, values tend to pile up around that t is 0. And for any alpha, we know that 1 minus alpha, the proportion of t values fall in between plus and minus t for appropriate degrees of freedom. So this is how we're going to do our calculate our confidence interval. For any mean with a standard error, that we have a certain mean, and we know the standard error, estimated standard error of the mean, we're going to pick an appropriate confidence interval. So if we pick an 80% confidence interval, the idea is that if it's 80% fall in here, meaning that 20% falls out in the tails. If we pick 90%, that means that 90%, we're confident that 90% of the values would fall in here, and 10% fall outside. If we pick 95%, same thing, 95% here, 5% in both tails combined, so on and so forth. Once we pick that confidence interval, our appropriate degree of confidence, we then use the t distribution table to find the value of t, period here, and then we solve the rearranged equation. And this is that rearranged equation. So I'm going to put these video clips that kind of are an example to help you understand what confidence intervals are a little bit better. So please watch those. I'll have some questions also posted for you to help you interpret the Price is Right games in terms of confidence intervals. But now we're going to go ahead and do all right, so now we're going to go through an example. So if you haven't already, or if you don't have it with you, go ahead and pause the video, pull out that teacher-led example, and try to complete it along with us. So we're going to do a 90% confidence interval. So if we have a 90% confidence interval, the idea is that we're confident 90% of the score will fall in here, which means if this is 90%, we have 10% left, right? So that means that 10% falls in these two tails, here and here. So %10 is going to give us a 0.1 probability in the two tails, or 0.05 in each tail. So we're going to use the t distribution table to find the value of t that we need for degrees of freedom of 7 and the alpha of 0.1. All right, so here we are at our t distribution table, and we need to go to degrees of freedom. So you see that part up there. Degrees of freedom of 7, which is here. And we want, in the combined two tails, 0.1. So that would be here. So that gives us a value of 1.895. So that's the critical boundaries denoting where our confidence falls. So we found out that our critical t, our boundary t, is plus or minus 1.895. So now we want to solve this formula to find out what our confidence interval is. So we're going to take the mean that we had, our sample mean was 9, plus or minus our t value, 1.895, and our expected standard error. And you can look at the problem up above at how you solved the problem earlier. So our S sub m was 1.18. So again, this value we just found, the 9 and the 1.18, come from the calculations we did earlier. So that's going to give us 9 plus or minus 2.2361. And that ends up giving us a confidence interval of 6.739 sorry, 6.7639 to 11.2361.